Good afternoon and welcome to Purdue University and the CERIAS Computer Security Seminar. Our speaker today is Mumurthy Murugesan. He's a PhD candidate working with Professor Chris Clifton. His topic today will be providing privacy through plausibly deniable search.
Oh, thanks, Randy, for the introduction. Good afternoon, everyone. I'm a PhD student, and as Randy said, in the computer science department. Here I work with Professor Chris Clifton. In today's seminar, I'm going to talk about web search privacy, how to provide users privacy in web search with a technique called Plausibly Deniable search. Okay, before we start, this small piece of a news article says what Google does with the search queries it collects over time, and does it combine the query logs with other information it has on you. So this is just to show that there's a concern among the public about web search privacy. Okay, in August 2006, AOL, American online company, released the web searches of its customers for basically research studies. The query log that they made public had almost 20 million queries of 650K unique users. So the anonymization they did was to replace the user ID with a random number. Okay, that's what they did. And the query log contained a timestamp and actual user query, and also the URL they clicked after getting the results. It happened that the anonymization they did was not sufficient. A New York Times reporter was able to successfully identify an individual who issued these queries. And some of the queries included 60 single men and landscapers in a particular area in Georgia. And also other queries included many specific information, so that that particular individual was identified by this reporter. What happened after that? It was an unfortunate incident, but it also created a lot of awareness about web search privacy, and the AOL fired the CTO because of this issue, and 2 researchers were forced out because of this problem. Okay, so what are the 2 approaches to handle web search privacy nowadays? So one is through server control privacy. The Google or Yahoo is taking care of the privacy of web search queries. So the first type, the search engine promises that, okay, I'll delete your queries after some time, or I'll anonymize the query log before backing up, after 9 months, after 12 months, etc. This is the normal procedure followed by companies such as Google, Yahoo these days. The other option is to use private information retrieval, in which the search engine will not know what exactly you're searching for. But what's the problem with that? It will affect the advertisement business model we have today, and okay, this solution is not going to work. Okay, so, and also we know that the search engines, they want to keep the query logs for a long time, right? That's what they are doing, and so that's what it's making some of these solutions not practical. Okay. The other type of solutions involve the user control privacy, in which the users will use these tools so that their privacy is protected. So there are a couple of tools available nowadays. One is the private web search from Yale University. It provides a complete package to block any metadata that is sent to the search engine nowadays. For example, you get your results and you click on a particular URL that you want to see. That information is sent back to the search engine, and if you use this tool, that kind of extra information that is sent to the search engine will be blocked. So they will, and also using such techniques such as onion routing, you can hide your actual IP address from the search engine. The second tool that is available, which is known as Track Me Not, it's a Firefox plugin that you can install in your machine. It's going to send out random queries every once in a while, so that the search engines will not be able to figure out, okay, what the actual queries are, what the actual user queries are. Uh, the idea used here is to use news headlines using RSS feeds and other famous queries. Kobe Bryant is a common query. Some of these search queries will be used as seed queries to construct other queries also. So the idea is that the search engine will not know what the actual user queries are. That's what they want to prevent here. So what is the problem here? You still are releasing your own query. The actual user query is still released to the search engine. That means your user intent, the user intent is also revealed to the search engine. Okay, so what are the lessons learned here? The information contained in the queries itself, they are enough to identify the user. For example, ego surfing, searching for your own name. A lot of us want to find out how famous we are, right? So we search our own name to see how many pages we are in, etc. And also looks like people search for SSN numbers and credit card numbers. And also how many times you should have searched Pizza Hut in West Lafayette. You might have done it a lot of times. And this applies to medical condition, some of the diseases you search for, and also many other details that you release in search engines are inherently, they can be used for identifying the individual. The second lesson learned is the fact that the query transformation, they transform the given query to something else so that you get what you want. It's not going to give you the privacy that you want. Okay, so what are the privacy issues here in web search? One is the identifiability. So I give you a query log. Can you identify the individual who issued these queries? That's the first question. Who issued these queries? And you can say, okay, this is John Smith, and I know this is Mumurthy Murugesan because he searched for his name several times over 6 months, right? So that's an identifiability question. Second question is linkability. The use of tools such as Track Me Not, you send random queries from your machine, and that leads to a situation in which the search engine doesn't know, oh, this query belongs to Mumurthy, or is it a random query, right? So you have a situation in which you have to map a query to the individual or to a particular identity. So here in this scenario, we're asking which queries were actually issued by John Smith. Okay, these techniques that I'm going to explain today is going to protect the users from the first problem, the linkability. That's the main issue that we're going to deal with. And also you have to realize that this is going to affect the identifiability, the first issue also. Okay, so let's move on to the main technique now. Plausibly deniable search. So you can see there are two terms involved, and deniability. So the users are going to submit not one query, k queries. And we have one more property that, which is called a reversible property, in which any of the k queries is going to give you the same set that you submitted. So you're going to submit k queries, and any of the k queries will would have produced the same query set. The additional queries that are included as part of your search query are known as cover queries, or masking queries. And also we make sure the way we build this query set, we make sure that these extra queries, the cover queries, are from different topics, not on the same topic that you are issuing your original query belongs to. Okay, second property is the plausibility. Okay, I'm going to issue not one query, k queries. But what happens if all my other queries, the cover queries, are implausible? For example, Java compiler and Newton Apple. Okay, these are two queries that I'm going to submit to search engine. But what about Java compiler and Motorola table? The second query, the Motorola table, looks like completely randomly generated query, right? So the implausible queries will weaken your deniability argument. So in this Java compiler Motorola table example, anyone who looks at these two queries will say, okay, Motorola table is out of the question, only Java compiler is actual query. So we need, when you submit these k queries, we need to have this plausible argument across all the queries. So the queries should be equally plausible. Okay, so this is a setup. What happens in the plausible deniable search. The user original query is Q3, and the user is generating this set of k queries. The set of queries are submitted to the search engine, and we call this set as a PD query set, plausible deniable search query set. Okay, once the search engine has the k queries, it could say, okay, I know you searched for Q2. Okay, that's a claim by the search engine. But you can say, no, I could have searched for Q1. Why? Because if I use the plausibly deniable search, the Q1 also gives me the same set, Q1 to Qk, which gives you the deniability argument. You can deny issuing any of the queries there in the set. And also, we have the property that all the queries are plausible user queries, the plausibility argument. Okay, so now we look at what are the characteristics of the k queries in that PDS system. So the first criteria is that we want each query in the PD query set to be a standard query. Okay, if you allow the user to create any possible queries, the spelling mistakes or the way you construct the queries will automatically lead to a situation in which one query will stand out from all the other queries. So you want to have each query to be a standard query. So that is the standardization we do before creating the set. The second is that deniability argument. For any query in the set of k queries, we should be able to get the reversibility. Any one of the k queries should be able to generate the same set, which will be issued to the search engine. Third criteria is the plausibility and diverse topics. So if one of my queries is related to basketball and the rest of the queries are also related to basketball, then there is no reason you have to use this technique, right? Because all the queries are on the same topic. So you need to have the diverse topic criteria. So all the k queries should be on different topics. Okay. So this shows the steps in this PDS system. The first step, you create a set of standard queries from a collection of documents. And the second step, you create this PD query sets based on the criteria we have defined. The query should be deniable, reversible property, and also the plausible property. The third step, what you do when a user, ordinary user, wants to issue a query, what do you do? So that's the final step we'll talk about later. Okay, the first step, creating canonical queries. Okay, so what are these canonical queries? Okay, these are the standard queries issued in place of the actual user queries. For example, basketball, NBA, or USA basketball could be replaced by a common query, more general query basketball. And also queries such as Purdue computer science and Purdue statistics could be replaced by a Purdue computer science statistics. So the canonical queries serve two purposes. One is that they do not reveal the actual query. They provide one level of anonymization. And second is that they replace the original query with a more related, semantically related query. For example, basketball NBA I should replace with basketball, not baseball, right? I want a similar query, and that's what the canonical query should achieve. Because you need to provide the users with the results they want, right? Okay. Now the question is, how do you create all possible canonical queries from a document collection, right? Because what we're saying here is that we pre-compute all these possible queries, and how do you do it? Okay. Let's say we have a document collection, M documents, and from the document collection we create this list of terms, N terms, and with that we can also create this term document matrix where each entry, A, J is the frequency of term I in document J. Okay. Once we have the list of terms, we can create this power set of this term set to create all the possible queries, right? That's a kind of obvious way, but which is not going to work because for large n, it is impossible to create all possible queries. Okay, the way we create this canonical query is by computing set of seed queries. What are these seed queries? Basically, they are single terms or term pairs that occur in the document collection more than delta times. We can delta could be 500 or 1,000 depending on your construction criteria. So what we are saying is that I know these single terms and these pair of terms occur more than 500 times in the document collection. That means they are significant to significant terms in the collection itself, right? Because they occur more frequently. So this to find the frequent terms, we can use tools such as frequent pattern mining, which are very efficient on the term document metrics. For example, frequency of IBM could be in the document collection could be occurring more than delta times, and also IBM DB2, because DB2 is a product from IBM, and jointly occur more than delta times. And also, single terms and the the term pairs are not sufficient to represent all possible user queries. So what we do, once we have the single terms and term pairs, we use a latent semantic indexing to kind of combine together the semantically similar seed queries to form the canonical queries. Okay, so if you don't know about latent semantic indexing, I'll just give a brief introduction here and then move back to the canonical queries construction. It's claimed that the latent semantic indexing is used by search engines such as Google these days. So it's an important IR technique. Okay, basically it's commonly used in IR to create concepts, concepts as in, topics from a document collection, so that terms and documents are related to set of topics or concepts. So the way it is done is used by using singular value decomposition. Basically, you decompose the term document metrics to 3 different matrices, so that the product of these gives you A. So the matrix U here gives you the relation between terms to concepts or terms to topics, and also the matrix V gives you the relation between concepts to documents. And instead of keeping, if you look at the size of U, it's n across n, but if you just keep R columns there, it gives you a representation, basically a concept space, which we can represent the terms in a concept space with using only R dimensions instead of m dimensions. So it's a dimensionality reduction. Also, it gives you a way to represent the terms in a topic space. So once you have the representation, you can compare topics of terms in this semantic space. Okay. Now, so we have a way of converting queries to points in the semantic space using this equation. And also note that the number of dimensions here is R, which is very less compared to m, the number of documents. Okay, let's go back to the canonical query construction. So we have the set of seed queries, and you want to create this canonical queries. So for each seed query, you find the other 2 closest seed queries in the semantic space. Basically, what I'm saying is that take a seed query, and what are the other 2 top 2 seed queries which are very similar in topic to this particular seed query. So you can use this based on the Euclidean distance between the seed queries to merge 3 seed queries together to form a canonical query. The example here, IBM DB2, it's a term pair which occurs, let's say, more than 500 times in the document collection, and also database which occurs more than 500 times. And in the semantic space, if these 2 are together, that means they are topically related, so we can combine them to create a new query, a canonical query, IBM DB2 database. Okay. So the canonical query representation, the use of canonical query is to, one is that you have several seed queries that map to this canonical query, and also the canonical queries are going to act as a semantically related surrogate query for the user query. Okay, so we have a set of we know how to create the set of canonical queries from a document collection. That's the first step. So that's done. Let's move on to the next step. Creating PD query sets. So the way we define the plausible deniable query sets with K queries, we need to have a procedure for creating that set. That's the next step. Okay, so the way we do it right now is to create a static linkage between K queries, K canonical queries. So any one of the queries will give you the K minus other cover queries. So it's basically a clustering problem. You have a set of canonical queries and you want to cluster them so that in each cluster there are at least K queries, and also all the K queries are from different topics, and we have the other criteria that all the K queries should be equally plausible. Okay, so this is a clustering problem, and the first thing is to define this dissimilarity function between any point. That's how we cluster the points together. And the dissimilarity function between queries here is based on three measures. One is the Euclidean distance. So we have the criteria that semantically similar queries are together. They are closer in the semantic space. So we are going to use Euclidean distance to capture that. If they are close in the semantic space, probably they are their topic is similar, right? So in a single PD query set, we want to have two queries which are different in their topics. So the Euclidean distance is going to capture that measure. So second thing is the magnitude. The popular queries will have, popular terms will have high frequency in the document collection, which leads to high magnitude in the semantic space. So we are going to use the magnitude for comparing the popularity of queries. The third criteria, we use the neighborhood count. So this is the important one. So we said we want to put equally plausible queries together, right? So how do you measure plausibility in for a query? So here we employ, so we take a query log, a large query log, which consists of all the actual users' queries collected over a period of time. And for each canonical query, we create a hypercube around that semantic the point of in the semantic space, and we compute how many user queries are around or in the neighborhood of this canonical query. So, for example, if you have a document collection with basketball, and I have a query Los Angeles Lakers, and if the semantic space is going to put the Los Angeles Lakers among basketball, that means Los Angeles Lakers is a famous query. It's more plausible query because there are many queries around the space of Los Angeles Lakers. Okay, that's the idea. So we want to use the existing query log to give an indication of whether a canonical query is going to be more plausible or not. Okay, that's a neighborhood count. Okay, so the dissimilarity measure, the score, is a combination of three individual normalized scores. So again, the D1 captures the Euclidean distance. If two canonical queries are apart, that means the topic is different. We are going to make the dissimilarity as 0 or lower dissimilarity. Again, the magnitude and neighborhood count. Here we want to have the if you look at D3, we want to have similar neighborhood count. In that case, if they are similar, D3 will be 0. That means we have a less dissimilarity if they have a similar neighborhood count. Okay, any questions? Okay, so the clustering algorithm is a simple one we have implemented. It's a simple agglomerative level by level clustering algorithm. So the input to the algorithm is the set of canonical queries and also K, K is basically the number of queries that you issue in place of a single user query. So to explain it, so the very first level you have all the individual canonical queries, and the next level you pair up the canonical queries which are closer based on the distance dissimilarity function we defined before, and you build up level by level. So this is the kind of a pictorial representation of what's happening here. So in the first level you have all the canonical queries, and in the next level you just find the pair of canonical queries which has the lowest dissimilarity score, and based on the same criteria you build on this. You merge the clusters level by level. Finally, it will lead to in this particular case 4 PD query sets. So if k is 4 or less than 4, you can stop here, right? Okay. So we know now how to construct a set of canonical queries, and also creating this PD query set for to be issued to the search engine. So next question is, as a user, I want to issue a query. Now, in this system, what happens? So this is the third step. Sorry. Okay. So we know a way to convert the user query vector to the semantic space or the topic space. So the formula we have already seen before. And so basically you find a canonical query which is very similar to the user query. It captures what you want. So that's a query you want to issue to the search engine so that you get what you want, and also you get the anonymity, right? So we use to measure the cosine similarity for finding the best canonical query that you want to issue. So we go through set all the canonical queries and find the canonical query which has the maximum cosine similarity. And next step is to find the PD query set that contains this canonical query. So you want to issue that set of k queries instead of your original user query. So that's the step. Okay, again to illustrate what's happening here, the first step. So user creates user wants to issue a query q, and the q is submitted to the PDS system, and you get set of k queries back. All the k queries are issued to the search engine, and the search engine will reply with the results for all the k queries, not one query, because the search engine at this point doesn't know what is your actual query. So it's going to send you results for all the k queries, right? So again, to remark here, it doesn't affect the business model, the advertisement business model here, because the search engine knows k queries and it can supply the advertisement advertisements for each of the k queries, right? So it's not that it doesn't know what you're doing, and it knows, okay, one of the k queries is your actual user query. So the search engine has the ability to send the advertisements related to each of the k queries. And the user, based on q, the small q, the user has the ability to filter out the results relevant to the original query q. Okay, so again, go back to this whole definition of plausible deniable search. The deniability is because the canonical query already provides one level of anonymity, right? Because you are going to issue only standard queries, not any constructed form of user query. And also plausibility, it's a more there has to be some kind of human study to see what queries are plausible, but the way we are doing it, based on the fact that a particular query is semantically related to many queries already issued by users from a query log. So the plausibility is also captured here. Okay, so the now question is, so you don't allow the users to form any query, right? Because we are going to issue only standard queries. How good are the canonical queries? Do they fetch what the users want? So that's the most important question now. So I'm going to report experimental results from a document collection, basically the document collection is a set of web pages taken from DMOS categorized web documents. Basically, this collection has category assigned by human editors for each web page. So here we took only around 300K documents, and it created about more than 1 million unique terms. And the documents belong to one of three topics: computer or science or sports. Okay, so and the computers had almost 115K documents, and it's kind of similar across all these three topics. And also, after performing the SVD, for the canonical the semantic space, we kept only 30 dimensions. Okay, so the first step is to create the set of canonical queries, and it created this procedure created 2.6 million C queries when the frequency threshold was set to 500, and it created almost 1 million canonical queries, where the length of the queries are listed in the table. Also, you should note that the average canonical query length is 3.7, which is almost 4, right? So you can see there are a lot of queries with 3 or 4 terms when compared to 6 terms or 2 terms. Okay, the first question is how many unique documents. So you have the whole documents with 300K documents, right? And how many documents the canonical queries can reach? When you issue the canonical query as a query, do they reach all the documents in the collection? That's the first question. So if you use the TF-IDF based simple retrieval scheme, you see that in the x-axis we plot the number of documents retrieved for each canonical query. So in the x-axis, so we compare the performance between 100 documents retrieved, 200 documents retrieved, and 500 documents retrieved. So if you retrieve 500 documents per canonical query, you can reach almost more than 99.4% of the documents in the collection. Okay, the next question is, okay, some documents are not at all reachable, even if you retrieve 500 documents per canonical query, and why it is that? If you look at the unreachable documents and their length, basically number of terms in that documents, it's low compared to the general collection. So the average document length, number of terms, in the whole collection is 360, but the average document length of unreachable documents, the documents which are not reachable by canonical queries, is just 35. So that explains why some of the documents are not at all reachable, because they don't have many terms to even be a significant document. Okay, second question. So the other aspect is the retrieval performance. So here, instead of submitting your original user query, you are going to submit something else, right? And does it fetch? What happens to the relevant pages that you get? Here, in the x-axis, we show. Okay, so using the original query, we retrieve 20 documents. 20 documents. We treat them as the relevant documents. Okay. Then using the canonical query, we retrieve 100, 200, 300, 400, and 500 documents, and find how many documents overlap in the top 20. Okay. So if you look at it, if you retrieve the very first column, where it indicates the x-axis, where it indicates 0, for 100, when you retrieve 100 documents, almost 15% of the queries don't have any match, 0 match in the top 20. But it decreases, zero match decreases as you increase, you get more documents, you retrieve more documents for each canonical query. And if you look at the last column, or to the right, the end of the x-axis where it indicates 20, for 500, it retrieves almost 15 percentage. It retrieves 20 of the top documents, which is very similar to what you get from your original user query. So you can see if you retrieve more documents, you can get. It's very similar to what you get from using your original user query. Okay, the second aspect of this is the topic diversity. So we said when you construct this PD query set, we said the query should be from different topics, right? So here we have three categories of web pages. One is computer science and sports, right? So we measured what is the topic diversity in a PD query set constructed based by the algorithm, right? So in the x-axis we show the topic diversity based, it's a kind of a normalized measure we get from the DMOS categories. So as it shows, around 85% of the PD query sets that are coming out of this algorithm have more than 50% of topic diversity. That explains different queries from different topics are put together in a single PD query set based on by the clustering algorithm. Okay, so I'm going to almost finish up now. Okay, so the PDA system, the summation of more than k queries can be used along with other tools we already saw, private web search, or even onion routing, so that you don't release your IP address to the search engine, etc. It can be used with those tools also. And the future work, for example, so we are saying we want to build all possible queries through these canonical queries generating algorithm. But how to do it efficiently? Currently for a collection of 300k documents, we have almost 1 million canonical queries, right? But for web search, it's a huge collection. It might increase the set of possible canonical queries to too large to maintain. So how do you generate all possible canonical queries efficiently? That's one aspect of this future work. And also improving retrieval performance. So you're going to replace your original query with a different query. Then how do you make sure that the transformed query will bring you what the original query will bring you? So you want to have a maximum overlap in that. So that's another aspect of this canonical query problem. The other thing is a sequential query. So the web search is also, the query log usually contains several sequentially edited queries. You search for something, then you edit it, right? You refine your query as you go along. So in that case, what happens? How the PDA system should work. It's again something for the future work. So if somebody takes a look at sequentially edited queries, can they figure out the actual queries even though they are using PDA system? So that's again something that we are working on. Okay, thanks. Any questions? Okay, then thank you.